We're into another video here in getting a feel for what titration is. We saw from the last video that acid-base titrations is the main sort of one we're going to be looking at in this series of videos here. But so let's get a feel for how do we conduct an acid-base titration. So in relation to our dot point here, we're hanging around here. We're still building up the concepts of what a titration is, so you know what to do it, and then we're going to look at it in detail. So let's get into an overview of how you conduct a titration, how do we use it to actually determine the concentration of an unknown, and some of the main key features. Alright, so what do we use acid-base titrations for? Well, mainly to find the concentration of an unknown acid or base solution. But we can also use it to find the concentration of a substance in a mixture. And so we might be looking at, can we determine how much phosphoric acid is in a soft drink? Or can we determine how much ethanol is present in a sample of wine? Because when they look at wine, they want to measure the total acidity content, and when they end up doing a lot of titrations. We might want to look at citric acid in lemon juice. And so these are the type of questions that we tend to get asked in the HSC. They're not very simple ones like the sodium hydroxide and hydrochloric acid. They're very simple, but of course they tend to give you these ones here. So let's look at the titration setup. Here is a typical titration setup. So the burette here is the device that will dispense a known quantity accurately of our known solution. Now our known solution is known as the titrant, and it is a primary standard. That is, it's a solution that we have made up and we know exactly the concentration of. And so we use this device here. We put that into a conical flask, and inside that conical flask we have a sample of the solution that's unknown. So we may have a sample of lemon juice and we put it in there. And that through that sample we also put in an indicator to change color, and then we add dropwise the known solution to the analyte, and that undergoes a neutralization reaction. And then when the neutralization reaction reaches a certain pH, the indicator will change color, and that'll tell us to stop adding the volume of our known solution. And so this is the general typical setup. So let's keep exploring this and get an understanding of how to do it, because it's not very far off. We're going to do one together. Alright, so here is how we could use it to find the unknown concentration. Let's say we have a very simple setup here, and the setup contains our known hydrochloric acid. So we have made up this solution and we know its concentration very well. We know it's 0.225 molar, and we also have a sample of our unknown solution down here, our analyte, and that unknown is sodium hydroxide, but we don't know its concentration. So what we can do is we can pipette 25 mils into there. So you can see we've got 25 mils, we don't know its concentration. And what we can do though is we can add our titrant, which is our known solution, our hydrochloric acid, to that, and that will allow us to use stoichiometry to determine its concentration. As you know from previous, if we know the number of moles of one reactant, then using the reaction ratios we can find out the number of moles of the other one. So if I said I had 1 mole of HCl, then that's going to react with 1 mole of sodium hydroxide to neutralize it. If I had to add 5 moles of HCl before it was neutralized, then that's telling you I must have 5 moles of sodium hydroxide. And so what we can do is we can use our stoichiometry. Now we know our relationship here between number of moles, concentration and volume. So if I now add my HCl down into my analyte, and I find that I have added 25 mils of that, then I can go, okay, how many moles have I just added to that conical flask to undergo complete neutralization? And we can rearrange this formula to go number of moles as concentration times volume. And in our sample right there, I know that my concentration is 0.225 molar times the volume, which is 0.025 liters. And that will give me an answer that is the number of moles present. And so that tells me that that's how much number of moles I must have with my sodium hydroxide. And then I can say, okay, I had my volume, and then using that I can work out its concentration. So that's the general principle of titration on a very simple level, is that we have a sample of unknown, the analyte in the flask, we have a sample of known in the burette, we add that to undergo a neutralization reaction. As that neutralization reaction goes, the pH changes. when it reaches the point at which we have neutralized the solution, then the reaction should stop, and we use an indicator to tell us that. Okay, so that's the basic idea. Now, I mentioned a second ago that we have an indicator to tell us to stop adding acid, because if you think about it, if we just had a normal beaker with our sodium hydroxide in there and we were adding some hydrochloric acid, as we're adding the hydrochloric acid, it's neutralizing the sodium hydroxide, and it will reach a point at which all the sodium hydroxide has been neutralized by the acid. That's where we want to stop, right? Because it's at that point, which is called the equivalence point, that we can use our reaction stoichiometry to do calculations, right? Because we know they react according to this ratio 1:1. However, if we keep adding the sodium hydroxide, we're now going past the point at which the solution has been neutralized, and we're just adding more and more OH minus. We could keep adding 700 liters of OH minus and still never know when to stop. So what we have to do is we have to put an indicator in solution, and that indicator will change color at a pH that is very, very close to the equivalence point, and that tells us to stop adding the acid. And so the one you can see here in the video is they started off with a titration with sodium hydroxide, so the indicator being used is called phenolphthalein. It's pink in sodium hydroxide. As they add the acid to the sodium hydroxide, right, it will change the pH environment of that conical flask. When it reaches the point at which the neutralization reaction has completed, that is, we have completely neutralized all the OH minus in there by adding the acid, when it reaches that point, then the color will change from pink to colorless, and that tells us to stop adding the acid. Okay, and as you can see that's what happens. And so indicators are used to tell us when we have reached the equivalence point in the reaction. Now, there's a difference between the terms equivalence point and endpoint. So equivalence point is the point at where the reaction has reached its end. In other words, the neutralization reaction has reached its end. We have added enough of the H plus to completely neutralize the number of moles of OH minus in solution to form water. Okay, the moles of titrant is equal to the moles of analyte that we have used, right? That's at the equivalence point. That's where we want to stop. The end point is the point at which the indicator changes color. And what you want to do is you want to choose an indicator that has a color change very, very, very close to the equivalence point. And usually we can do that within one drop. And so that's pretty good when we want to do our calculations, right? So that is the difference between an endpoint and an equivalence point. In this example here, you can see we've got some phenolphthalein because it's pink. Now it's below the endpoint. That means at the beginning of the titration, it's colorless. So in this example here, we have H plus in our analyte. So we're analyzing a sample of acid. We are adding OH minus to it. So as the OH minus adds to the H plus to form water, it neutralizes. And when you add the OH minus, you'll notice that a little section of it turns pink, right? You can see that in the video here. But when you keep swirling, that pink disappears, right? So that's telling you you're below the equivalence point. For phenolphthalein, the end point of the indicator is 8.3, and so when we reach the pH of around about 8.3, 8.2 to 8.3, then we have a color change and it stays pink. Very, very faint. That's telling us we have reached that pH level. Therefore, stop adding. If we keep adding our OH minus, then we're going to get past our endpoint and we're going to add too much of our titrant, right, the OH minus. Therefore, that's going to give us an inaccurate calculation of how much H plus was in the flask. So make sure you stop at when you have a faint pink color. All right, so we've talked about titration. We understand how it works generally. Let's talk a little bit about how we use some of the equipment here in our titration. Remember, we said we had to put the analyte into our conical flask. Well, of course, we've got to do that in a very precise way. And so what we do is we use a volumetric pipette. Here it is. You can see this one here is a 25 ml volumetric pipette. They are calibrated to be extremely accurate in measuring volumes. And so we want to make sure we use the correct technique and these equipment correctly so that we can dispense the analyte into our conical flask. And so we've got our pipette bulb filler here. You've probably used these a lot in your lab. You can see we've got A, you press A, squeeze this, the air gets removed from the bulb. That creates a suction up here in the bulb section. You've got your pipette attached. When you place your pipette into a beaker of your analyte, then you, of course, press the S, which is siphon, and which sucks up the solution. Now, you don't put your pipette into a stock solution because that may contaminate the stock solution. You pour some of the stock solution into a beaker, and then you draw up your liquid from the beaker there. And then, of course, we can use E to empty that into our conical flask. When it comes to the end of that and dispensing the liquid, you just release the liquid into the conical flask, and then you place the tip of that pipette on the side of the conical flask to ensure that the volume is accurate. Okay, so that's how you do that one. So we've looked at what volumetric techniques are used in titration, acids and bases. Hopefully you had a better feel now for what an acid-base titration involves, how that works with the equation using stoichiometry to calculate the unknown. Don't worry, we're going to go through all the calculations in detail with examples in future videos, but this is to give you a feel for the technique and how we use it. Of course, as always, make sure you do the worksheets below and the Kahoots. And if you are part of our course, we've got the titration posters, we've got our flashcards, and of course, if you're not part of the course, come over and join us. Click like and subscribe if you're here on YouTube, and I'll see you in the courses for more chemistry. And of course, if your school is not a subscriber, you can always purchase these at thecrazyscientist.com. Heaps of resources there, and I'll see you in the next video.